Acyloin condensation. We all know that condensation means if two reactants are combined together to produce a particular product by the elimination of simple molecules like H2O, HCl, we can represent this is HX, simple methanol. Such type of reactions are commonly called as what? Condensation reactions. So, Acyloin condensation is an example of a condensation reaction. Already we know that the format for easy remembering of any kind of chemical reaction where the first component is what? Statement. If you see the statement of Acyloin condensation, this is the statement of Acyloin condensation. Conversion of esters into alpha hydroxy ketones using metallic sodium in presence of aprotic solvents. In this particular condensation, the reactants are what? Esters. The reactants are converted into what? Alpha hydroxy ketones. So simply the representation is what? Conversion of esters to alpha hydroxy ketones in presence of what? Metallic sodium in presence of aprotic solvent. The aprotic solvents may be benzene, it may be toluene, it may be xylene. These are the solvents generally used as aprotic solvents for this conversion. Right? The second component in the format is what? General equation. How can we symbolically represent the conversion of esters to alpha hydroxy ketones? General equation. The simple representation of ester is what? RC double bond OR dash. Here we have taken sodium, for example, we have used the solvent xylene initially. So it will come up with what? R single bond COH, H single bond C double bond OR. This is the what? Alpha hydroxy ketone. We have two functional groups here. One is the OH and another one is C double bond O. When two different functional groups are in competition, we need to have this one is the main functional group, that is a ketone. With respect to the ketonic carbonyl, the first carbon is alpha carbon, it is having OH group, that's why we are saying it is a alpha hydroxy ketone. Here this R group is aliphatic one. If the R group is aliphatic, This alpha hydroxy ketone is commonly called as acyloin. Acyloin. Let's see the mechanism of this particular transformation. Before discussing about the mechanism, here we need to identify one thing, that is the number of moles of the reactant must be 2 moles. In this transformation, we need to take 2 moles of the reactant, then only you will come up with alpha hydroxy ketone. Otherwise, it is not possible to have acyloin, right? Right? Let's see the mechanism. We know that generally mechanism is 2 types. The first one is ionic mechanism, second one is free radical mechanism. In order to identify the mechanism, we are having cleavages: homolytic cleavage and heterolytic cleavage. In case of homolytic cleavage, what happens? If you cleave a bond, it can produce what? Radicals. But in case of heterolytic cleavage, you will come up with what? Ions. So the ionic mechanism proceeds through the formation of positively or negatively charged ions. But in case of free radical mechanism, we are identifying the what? Free radicals. This particular acyloin condensation, here we are observing the mechanism called free radical mechanism, not the ionic mechanism. Why? Because here we are using a component called as sodium. Sodium metal we have used. In most of the cases, whenever we use a sodium or any kind of metal, the mechanism proceeds through the formation of free radicals. Let us see. The reactant is what? Ester. RC double bond O, OR dash. This is the general representation of ester. The ester is treated with what? Sodium metal. Already we know that the sodium can readily lose 1 electron to produce Na plus ion. Na plus ion is the stable form of sodium. According to the general equation, we need to take 2 moles of ester. That's why 2 moles of sodium is needed. So 2 Na plus and 2 electrons. So initially sodium loses its 1 electron to produce Na plus ion with the formation of an electron. We are saying that the mechanism is what? Free radical mechanism. Free radical mechanism. It is necessary to generate free radicals in your reactant. The reactant is the what? Ester. In ester we are having carbon-oxygen pi bond. The carbon-oxygen pi bond is subjected to homolytic cleavage. So the homolytic cleavage of this particular bond creates what? RCO radical and C radical with OR dash. Now we are having electrons here. This particular electron may approach oxygen or it may approach carbon. It means that what? We can generate minus charge either at oxygen or either at carbon. The feasible one is what? R single bond CO minus. Why? Because comparing with the carbon, oxygen is more electronegative in nature. That's why the minus charge is going to be formed at the oxygen only. So it can creates minus charge at the oxygen and we have RC radical and OR dash. This is with one reactant, but we have two reactants. That's why these kind of species are going to be produced, right? The second species, what? For the convenience, I am writing the second species in this way: O minus OR dash and R. Okay. Two Na plus ions move towards what? This oxygen negative charge or not? One Na plus ion with the first O minus, the second Na plus ion with the second O minus. Now what happens? These two radicals can form a carbon-carbon single bond. This we can say that it is a coupling. So through this coupling, what we are getting? RCO minus Na plus CO minus Na plus OR dash, and this is R. This O minus is going to form a carbon pi bond and it can remove OR dash minus. This OR dash minus and this Na plus combine with each other to produce what? R dash ONA. Here also similar situation. O minus forming a pi bond and OR dash minus will be removed. This OR dash minus and Na plus to form another molecule. That's why here we are observing what? 2 moles of R dash ONA. We can write the molecule RC double bond O, C double bond O, R. This is an intermediate in this particular reaction. This is the what we call diketone. 2 ketonic groups are present. That's why this is the what? Diketone. The diketone is the intermediate in this transformation. Already we know that we have sodium metal. Again 2 C double bond O groups are present. That's why we need to take 2 moles of Na. It can produce 2 moles of Na plus with 2 electrons. These 2 electrons again move towards the oxygen. Why? Because here we are getting the oxygen radicals. The oxygen radicals can form what? O minus R radical and a radical. The 2 Na plus ions move towards O minus. These two can form a pi bond. So we will come up with what? R single bond CO minus Na plus double bond CO minus Na plus and R. This one is subjected to hydrolysis. It can produce RCOH, double bond COH. The formed product is subjected to tautomerism. It can produce the final product RCOH, CH, C double bond O, R. This is the what? Acyloin. In this way we can transfer the ester into the corresponding acyloin. Through which mechanism? Free radical mechanism. The last portion in this particular reaction is what? Applications. Let us see the applications. The first application is CH3, CH2, CH2, C double bond O, OC2H5. This is one ester. We need to take 2 moles treated with sodium in xylene followed by hydrolysis. The product will be CH3, CH2, CH2, C double bond O, CHOH, CH2, CH2, CH. For the simplicity, what can we identify easily? Simply take this moiety 2 times. These 2 chains connect with 2 carbons. One carbon must be keto group, another carbon must be OH. In this way, you need to remember the examples. If you observe the particular application, we have taken 2 moles of ester, right? It means that 2 C double bond O groups are present. One C double bond O group is present in the form of ketone, another C double bond O group present in the form of OH. It means that what? This is the reduced form of C double bond O or not. That's why this particular condensation is the example of reductive coupling. Reductive coupling. We have seen the mechanism where 2 C radicals are forming a single bond. That is the what? Coupling. That's why this is an example of reductive coupling. In generally, this particular reaction is useful in the synthesis of cyclic compounds. If you want to synthesize the cyclic compounds, the Acyloin condensation is the best example. Let's see some of the applications related to the formation of cyclic compounds. The reactant is C double bond OC2H5 and C double bond OC2H5. Sodium, xylene followed by hydrolysis. For Acyloin condensation, we need 2 ester moieties or not. If you see this particular example, both the ester groups are present in the same molecule. In previous example, we have taken 2 molecules, but here 1 molecule containing 2 ester groups. That's why this particular reactant can be subjected to Acyloin condensation. So simply what happens, 1 ester group must be converted into C double bond O, another ester group converted into OH. 1, 2, 3, 4. This is the 5th carbon. This one is the what? 6th carbon. Simply what happens? The cyclization phenomena takes place. One is converted into C double bond O, another is converted into OH. The products are what? Alpha hydroxy ketones. See this? With respect to C double bond O, it is the alpha position containing OH group. That's why it is the what? Alpha hydroxy ketone, but it is in the what? Cyclic form. It means that what? This particular condensation reaction is useful for the synthesis of cyclic alpha hydroxy ketones. Let us see one more example. Single bond CH2, CH3, COO, CH3 and CH2 thrice COO, CH3. Under same conditions, CH2, CH2 thrice, CH2 thrice. One carbon must be what? C double bond O. Another carbon must be what? OH.